Hello everyone, my name is Fatih Deniz and I'm going to talk about our paper titled Detecting and Mitigating Sampling Bias in Cybersecurity with Unlabeled Data. This is a joint work with Qatar Computing Research Institute and Palo Alto Networks. This is the outline of my presentation. I'll start with the definition of sampling bias and the types of errors that we handle within the scope of this study. I'll mention how prevalent sampling bias is in cybersecurity and what are the main causes. Then I'll continue with our approach. We divide the problem into two as detection and mitigation. They can be used independently. I'll mention our novel solutions for both. Our solutions align with the demands of cybersecurity. In cybersecurity, labeling is costly, so we're using unlabeled data. In cybersecurity, there are several types of classifiers, so our approaches are classifier agnostic. I'll conclude with the results. We have tested our algorithms in diverse benchmark datasets from intrusion detection systems, Microsoft PE, Android malware, and malicious URLs. There are really tons of tricks we have applied. So here I'll try to give the main idea, but for details, please refer to our paper. Let's start with the definition. Sampling bias means the collected data doesn't sufficiently represent the true data distribution of the underlying problem. So in other words, training and deployment data distributions are not the same. So what happens if they're not the same? In our papers, we provide great results, but when we deploy our models into production, we fail miserably. Due to its prevalence, sampling bias is a very important problem in cybersecurity. As indicated 2 years ago in USENIX 2022 in Boston, sampling bias is the most prevalent issue while using ML in cybersecurity. 90% of the analyzed 30 top-tier conference papers contain sampling bias. Actually, cybersecurity is unique from certain points. We are always working in an adversarial environment. Adversaries try to hide themselves, and that is why feature collection is not easy. Labeling is costly. That's why we rely on heuristics, and that significantly increases the sampling bias. So in this paper, our focus is representation error from the total survey error framework. It consists of three key sources of error: coverage error, sampling error, and non-response error. Since this terminology is coming from the statistics community, I will try to explain it with an example from cybersecurity. Coverage error occurs when sampling frame is not the same as the target population. Here, target population is the set of all URLs, but the sampling frame consists of public URLs, ignoring the private URLs. And sampling error occurs when the subset of data items chosen from the sampling frame is not representative. Given the set of all public URLs, if we can only collect data from our regional DNS servers, the selected sample will not be representative of the sampling frame, so this will cause sampling error. Finally, non-response error occurs if a non-uniform subset of the observed sample is excluded. For example, if we are using some labeling heuristic, and if we label if a URL is not detected by any of the VT classifiers as benign and K+ detections as malicious, we are going to ignore the ones in between, and this will cause a non-response error. In this work, we handle all these three types of errors. I'm not going to get into detail, but existing work has studied the specific cases of sampling bias. But here we are directly and systematically attacking the general problem. One key insight here: unlike concept or distribution drift, sampling bias exists before the classifier is deployed, and that is why addressing it requires different strategies. So let's start with the problem definition. We split the problem into two as detection and mitigation. Given a labeled training dataset DT and the classifier that is trained on it, we have the deployment data. Their distribution might match or doesn't have to match. Here our objective is twofold. First one is detect if this trained classifier is biased or can be used in production. Here we're especially interested in detecting malignant sampling bias, meaning that whether this classifier will perform suboptimally or optimally in production. Our second objective is, if there's a bias, train a classifier with a higher performance in production than the CT. So let's dig a little bit deeper. Let's start with the detection methods. To detect sampling bias, we propose two algorithms based on domain discrimination and distribution of k nearest neighbor. We mentioned we are interested in detecting malignant sampling bias, but such that the classifier has suboptimal performance in production. At this point, if you had the labels from the production, it would be easy. So we're just going to measure the accuracy and it would be easy. But we don't have the labels, so we have to do it without the labels. That is the challenge. Let's start with our first detection algorithm. This is based on the concept of domain discrimination. Our intuition is, if training and production data cannot be differentiated, then there will not be sampling bias. So for that, we train a classifier to determine if data items belongs to training or production. All the items from training have a label of 1, and all the items from the deployment are 0. So using this labeled data, we train a classifier, and the aim of this classifier is to distinguish whether a data point belongs to training or deployment. If the accuracy is low, such as twin cost 0.5, then we cannot distinguish the source of the data, which implies there is no sampling bias. But if the accuracy is high, meaning that the distributions are substantially different, then there will likely be a biased classifier. It's very simple and it works in practice. Our second and more effective detector is KNN-based bias detector. Our intuition is, if two data distributions are similar, then the distribution of the distance to the k nearest neighbor will also be similar. Here, we train an autoencoder using supervised contrastive learning approach. It ensures same class embeddings are grouped together and embeddings of data items from different classes are pulled apart. We obtain corresponding and normalized embeddings for the training data using the autoencoder, and then we compute the normalized embeddings for the deployment data. So in a way, we are creating two sets. And as a last step, we compute the distances between normalized embeddings to the corresponding embeddings of the label set and compare these distributions. If these distributions are different, we say there's a sampling bias. In this study, we only compared the median values of these distributions against a threshold, but we believe, since we do have a distribution, a series, there might be better approaches to detect the differences between these two embeddings. So let's continue with the mitigation methods. For mitigation, we propose two novel algorithms, both based on the self-training paradigm, but we cannot use the self-training approaches designed for the computer vision or tabular ML. Computer vision often relies on label preserving transformation. For instance, a rotated image of a cat has a label cat. Or in tabular ML, they create transformation through controlled feature corruption, like changing a tuple from another tuple. But this approach is not label preserving, as cybersecurity classifiers are often more sensitive to individual features. In both approaches in both of these mitigation strategies, we are using pseudo labels. But when you use pseudo labels with the feature space, we observe that you only poison your model and this poison model do not perform well in practice. Our clever idea here is to use geometric aspects of ML classifiers over the embedding space and design an encoder that better maps the data points. For instance, if you train a KNN classifier is non-parametric and it has very complex decision boundaries, and when you check when you find a very similar data point, it can be classified as the other class label. So let me quickly review these approaches. Our first mitigation algorithm uses contrastive learning on the unlabeled data. The key challenge is to identify positive and negative pairs without having the label information. We achieve it again by using pseudo-labels, but while running this algorithm, we also train an encoder to map similar items to the same embedding space. As the first step, we compute the embeddings of the label set and compute pseudo-labels according to the nearest centroid values for the production data points. Then once we have the set of positive and negative sample pairs, we then train a contrastive encoder. And as the loss function, we use soft neighbor loss. And we also combine it with the cross-central loss for the labeled dataset. The second one is based on the iterative approach. So like in this one, we would like to estimate the pseudo-label accuracy. So we would like to use high-quality labels, but we don't have the labels for the use, so we cannot estimate the pseudo-label accuracy for our labels, generated pseudo-labels. So our solution is to use interrelated classifiers. So we are using the trained classifier for generating the pseudo-labels for the production data. Then by using these pseudo-labels, we train another classifier and obtain predictions for the labeled dataset. So in a way, indirectly, we are measuring the accuracy of these pseudo-labels. So let me also briefly mention about the results. We conducted our experiments over widely used benchmark datasets from Android and Android malware, Microsoft PE, introduction detection systems, and malicious URLs. We trained our cluster using one dataset, evaluated user another dataset not to cause any bias. We tried so many scenarios with different classifiers and different sampling strategies. And in general, even in the adversarial setting, we could reclaim 10 to 16 points in deployment F-score. I'll also quickly mention about our findings in a minute. So, as you can see, both of our approaches can detect sampling bias. Here there are the baselines. Our detection approach is classifier agnostic. We tried multiple classifiers. We observed that we can mitigate over 90% of the adverse effects of sampling bias. You can observe cyclic bias detection works better than the contrastive learning-based approach, but it works slower than it, so we kept using both of them. For mitigation, our approach works for different sampling strategies. And our mitigation approach is also classifier agnostic. As a conclusion, sampling bias is a very prevalent issue in cybersecurity, and we address them both detection and mitigation with very high accuracy. We can detect sampling bias and reclaim 90% of lost deployment F-score. Thank you very much. If you have any questions.